Baseball is a game that has many important statistics and features that one could predict, but the most important out of these is clearly pitches. Baseball has many distinct pitches, but knowing what pitch can come and knowing the break that it will have will give you a distinct advantage in hitting. Out of the pitches, there are five that are the most common. Fastball, which is a fast pitch that goes completely straight. Curveball, which is a slow dropping pitch that goes from 12 to 6 o'clock. Sinker or two-seamer, which is a hard-driven pitch with drop. Changeup, which is a slow pitch that looks like a fastball for most of its trajectory before slowing. And slider, a pitch that breaks inward and downward. With all these pitches, there's similar release points and initial trajectories, but then they change depending on what pitch it is. There are also other closely related pitches which also need to be categorized. In order to solve this problem, we attempt to create a model that predicts the next pitch type that will be thrown based on the game's current situation. Our model is generalized across MLB pitchers and is intended to be deployed for amateur teams in real-time games. For pre-processing the data, and acquiring the data, we acquire the data from PyBaseball StatCast, which is basically a Python library which pulls from MLB StatCast data, and we pulled all the pitches from June 2021. This gave us 34 different pitches along with the pitch type, which was our target value. We removed pitches which were unknown, knuckleballs, slow curves, ephesus, and pitch outs because these pitches are irrelevant to hitters and are either unknown or 100% thrown given in a situation. Then we replaced all text values with one hot encoding, so 0 and 1 for handedness of the batter and pitcher, and 0 through 29 for team values. We merged pitch types which are functionally the same to make classification easier, and also because hitters don't really need to differentiate between them. Splitter to sinker, slider to sweeper, and slurp to curveball all became merged. Lastly, for runners on base, we replaced the player ID with just a 1 if they were there and a 0 if not there. And for pitch types, we replace them with numbers for easier prediction. And for dates of the month, we replace them with the days of the month since they were all from June.
I did some research on different work that other people have done on similar topics. So the first one here was an article on Medium. They used 3 seasons worth of data to train a support vector machine, and they got about 68% accuracy with it, which is pretty good, but they were just doing binary classification. So instead of classifying four-seam fastballs, sinkers, cutters as separate pitches, they were just calling all of those fastballs, and then they were classifying fastballs versus non-fastballs. So their task was easier than what we're doing, so I'd expect their accuracy to be a little bit higher in the end. Second one I looked at was written by 2 researchers. They wrote a paper where they trained random forests and got 60% accuracy. But what they were doing is training a separate model for each pitcher, which requires a bunch of a priori knowledge. That's not really our objective. Ours isn't intended for the MLB where this information is available. Ours is intended for amateur teams where they might not have that. You just want to be able to throw our model in and say, here's what the game situation is, predict the next pitch for me. So I'd expect our accuracy will be a little bit lower than theirs as well. The last one I looked at was a blog post written by a guy named Josh Mancuso, and he actually did something pretty similar to us, but he was only able to get 45% accuracy. We actually got a little bit higher, and ours is more well generalized because he was only training on 4 MLB pitchers. Ours is trained on all MLB pitchers, so I think ours is a little bit better suited for just a general situation with an amateur team. So the first model we tried was based on the k-means clustering algorithm, and it uses the assumption that there are certain situations in which a pitcher will almost always throw a certain pitch. So the first 2 here are the first pitch of the game, and when the count is 3-0, the pitcher almost always throws a fastball. And then this last graph is kind of an exception. This is when the count is 0-2. The pitcher kind of has more freedom to throw what they'd like. So what this algorithm was doing is it's applying a standard scalar and then a train test split. And for each pitch type in the training data, all the pitches of that pitch type were clustered into 3 different clusters. And for each test sample, the closest cluster was found, and the associated pitch type was guessed for that sample. And this didn't do very well. It got 18% accuracy, which is pretty bad, but it did do much better on those 2 specific test cases that I mentioned on the previous slide where a fastball is almost always thrown. So I think the assumption was just off from the beginning, and also I think the model was a little bit too simple. But I still liked this. I thought it was a novel idea. K-means isn't usually used for classification, so I liked the idea.
Our team also tried out the classification models we used during the Kaggle competition. For all models, we defined a parameter grid for grid search or randomized search to find the best model parameters and used ROC, AUC as our evaluation metric. We started off with logistic regression since we have imbalanced classes in this data set, we set the class weight parameter to balanced, which in effect assigns higher weights to minority classes, helping the model learn them better. After finding the best model parameters, we achieved an AUC score of 0.565. We then used the random forest classifier. We observed that the n estimators and max step parameters were the most impactful in terms of AUC score. After cross-validation, we were able to achieve an AUC score of 0.7631, which was significantly better than the logistic regression model. We also applied the XGV boost classifier and were able to get an AUC score of 0.8265, which outperformed the last two models by a large margin. This classifier was largely effective in the situation because of how many features we had in our data set. The team also tried other classification methods, and similarly we defined a parameter grid for grid search to find the best model parameters and use ROC AUC as our evaluation metric. We used a decision tree classifier, but it wasn't very effective for our data set. We were able to achieve an AUC score of 0.7536, but the non-linearity of our data set could have caused the poor performance. We also used a bagging classifier, which gave us an AUC score of 0.7828, but again here, the data imbalance could have been a cause of the poor performance. Some research suggested trying the support vector machine, but it was much more effective for a limited range of hyperparameters, and for a large data set, the solution would require a significant amount of computational resources. One of the most effective classification algorithms for us was gradient boosting. The model achieved an impressive ROC AUC score of 0.8465. Its ability to handle complex nonlinear relationships in the data and its capacity for handling large data sets made it a popular choice for a variety of classification tasks. We also created a confusion matrix, and we can see that the first class of fastballs was the most frequently thrown pitch in the entire data set. For the other classes, the scores were not nearly as dark, but this wasn't necessarily indicative of the accuracy of predicting those pitches due to their lower frequency in the data set. Cat-boost modeling also proved to be very effective for this baseball pitch problem. Our best score from cross-validation was an ROC AUC score of 0.8523. Similar to gradient boosting, we made a confusion matrix and saw here as well that the first class of fastballs was the most frequently thrown pitch in the entire dataset, giving it a very dark square. For the other classes, the squares were not nearly as dark, but this wasn't necessarily indicative of the accuracy of predicting those pitches because they had a lower frequency in the dataset. To get a more comprehensive evaluation of the model performance, we also computed other metrics like precision recall and F1 scores for each class. We also tried the auto boost algorithm on this dataset. We were able to achieve an AUC score of 0.7512. To get a more comprehensive evaluation of the model performance, we also computed other metrics like precision recall and F1 scores for each class. The results showed the model struggled to classify the minority classes, which could have been a result of the class imbalance in the data set. It also uses a weak learner as a base estimator to build an ensemble model, and while the simplicity can be advantageous in some cases, here it limited the model's ability to capture the complex relationships between the features in this large data set. Our team also attempted to use transfer learning with neural networks. Transfer learning is a machine learning technique that enables the reuse of pre-trained models' knowledge and expertise to improve the performance of a new model on a related task. In our multi-class classification problem, we thought of using transfer learning to take advantage of the pre-trained model's knowledge on similar tasks and apply it to our own problem. Instead of training our problem from scratch, we used a pre-trained model, TabNet. We were able to only achieve an AUC score of 0.5192, so we attempted to improve the model's performance by adding additional classification layers, but we faced installation issues with PyTorch and TensorFlow.
As part of our results, we also decided to calculate feature importance using Cat-boost, which is our most successful model. Out of the most important features, we found that who the pitcher was, how they threw, as well as different features of the team, such as who the fielders were found to be the most important features. This suggests that it's actually a function of who the team is and how they like to field that also plays a key role in determining what pitches are thrown. To break down the contributions of who did what, Jason, was in charge of obtaining data, pre-processing, feature engineering, results analysis, and part of the video. Rick was in charge of the k-means model, prior methods research and summary, and part of the video. Manav calculated accuracy score, did method research, and did moving the report to Medium. Berk was in charge of XGBoost, decision tree, bagging, and gradient boosting. Gizem did Cat-boost, some part of feature engineering, and transfer learning with neural networks, while Onat did logistic regression, random forest, and AdaBoost. As you can see, we've shown a graph of our best models, ROC, AOSCI, 1 versus rest score, and we found that gradient boosting and cap boosting worked the best, with cap boosting offered the best value. For future works, we could test the model with real pitchers, create a front-end app to gather real data, or combine situational features with scouting features, such as pitchers' frequency of throwing pitches, as well as statistics, such as ERA.